The next presentation is going to be Arindam Sakari is going to be presenting on dual attention higher order factorization machines.
Hi everyone, I'm Arindam Sarkar, and today I'll be presenting dual attentional higher order factorization machines, which is a joint work with my colleagues at Amazon, Dipankar Das, Vivek Sembiam, and Prakash Komar. So, multiple ML problems of practical significance. They depend on complex feature interactions. For instance, in an e-commerce marketplace, when a customer comes to purchase an item, their choice will depend both on the product category and the pricing within the category. They might also look at the review rating and compare the product relative to the other products in the same category and in the same price range. So these are examples of higher order interactions that go into a user choice. There is another popular example in the literature which tells that in the app, if you look at the app download behavior of male teenage gamers, they are found to be preferred shooting games or RPGs over other category of games. Now, all of these feature interactions, so how do we represent them? So the first and the simplest one is that we explicitly engineer the higher order features. And in fact, this is one of the most popular approaches. So given a feature set, let's say the scalar x, y, and z's, the higher order interactions could be the pairwise interactions or the three-way interaction of the features. However, as evident, this gets combinatorially expensive to do as the number of features increases. The second is leveraging the higher order feature combinations automatically, which is done by polynomial kernel based regression and factorization machines. And then we have our neural networks, which by iteratively projecting the linear combination of features into nonlinear spaces learn the higher order interactions. Now let's take a quick look at how do we modeling interactions with factorization machines. So for a factorization machine of order or degree 2, this is the equation of the model. So first term is the bias term. The second term is simply the linear combination of features. And the third term here is the pairwise combination of features. VI's are the latent space representation and XI's indicate the presence of a feature, that is its one-hot encoded representation. Now, if we look at the second order term, we can clearly see that because of this nested summation structure, it has a quadratic complexity. However, the FM paper suggested an efficient solution which is linear in complexity. That is, by simply expanding this term out, we get the double summation term while avoiding the quadratic complexity in here. Now the parameters of the model, for example the W's and the VI's, these can be estimated by gradient descent. So before we proceed further, there is one interesting question that one encounters, and that is, when would we want to use factorization machines versus neural networks, since both of them seem to be approximating the higher order interactions? Let's take a look at a synthetic example to get an intuitive feeling about the same. So we get two features x and z sampled from uniform distributions, and then we have the response variable y, which is modeled by a Gaussian with mean coming from this quadratic polynomial term. In this plot, we see the performance on the synthetic data where we train a neural network highlighted with the stars, and we train a factorization machine. The neural network parameter sizes are given in the brackets. So 10 here means that there are 10 hidden neurons in the hidden layer. Whereas for the factorization machine, we have a constant parameter size of 4. Because of the way this function is designed, it takes a much larger neural network to get the same level of performance in terms of mean squared error on the test set as a small factorization machine. So while neural networks and factorization machines are modeling the same class of function here, it's more efficient to use the factorization machine because of the design of the function here. In another example, we have the same design. However, we replace this function with a non-linear projection of linear combination of the features. Here, as we would expect, factorization machine is outperformed by the neural networks of much smaller sizes. We will utilize this fact later going on in this presentation. So before we proceed, let's take a look at what can we do with a factorization machine of a higher degree. So as we would expect, these can effectively model higher order interactions like multi-way product of features. Because of the latent space representation, even if two features never co-occur in the data, during inference, these can still capture the effects of interaction. And because of the attractive properties, these have been a popular choice in domains with sparse data, for example, click-through rate and conversion prediction. So for a factorization machine of higher order, the original paper does not suggest an efficient solution, and if we simply extend the approach of degree equal to 2, we get this nested summation structure, which when solved naively is of exponential complexity. So in this work, based on the past work in the literature, we propose a novel way of modeling the higher order interactions. So the way we do it is by modeling higher order terms as composition of lower order ones. So this is the core idea behind the work. We have a multi-layered network, and at each layer we compute a representation of all the terms of degree of order L plus 1. So what this means is, to compute interaction, let's say of order 3, we simply multiply the order 2 representation of the same feature I with the order 0 terms. So this gives us, or basically this summarizes all the interactions with feature I of degree L plus 1. So this essentially allows compression of interaction information for one particular feature. Now, one thing we note here is that all interactions from the previous layer's representation, they get equal weightage. This can become an issue sometimes, and as we also observe in our experiments, when there are feature pairs which did not co-occur in the data during training and thus leading to overfitting. This can be simply solved, or let's say be mitigated to a certain extent, by using attention-based architectures in which we suppress interaction terms which have low relative value. So we simply introduce this term alpha here, which is just a linear projection of the interaction terms. So far, we have at each layer the higher order representation of a given feature which summarizes its interaction with all the other features. Now, to get all the terms of order L, we use attentional pooling, and this now gives us a way to aggregate all the interactions up to a degree L. So in this work, we simply concatenate all of these Z terms, and this thereby captures, or rather summarizes, all the explicit interaction terms. Now, as we saw a few slides back, that there are cases in which the neural network could be more efficient to learn compared to a factorization machine and vice versa. And this has also been used and observed by the other works in literature. And in the same vein, we leverage a neural network to capture these so-called implicit interaction terms. So the final representation is the concatenation of the explicit and the implicit interaction terms followed by a linear projection. This is our architecture at a glance. Starting from the input layer, we have a series of attentional interaction layers, and summarizing the interactions via attentional pooling, and finally concatenating them and passing through a linear layer to get the final representations. Now, one potential issue with the softmax function we have used here is that the output of softmax, it consists of non-zero terms. So what could happen is that all the higher order terms, even if they have very small weights, they can end up becoming part of the final representation. This might sometimes result into accumulation of noise interactions. To mitigate this issue, we introduce sparsity via this sparsity inducing normalizing function. In our case, we simply use softmax with a temperature term, in which as the tau tends to 0, the distribution becomes more and more sparse. In our experiments, we observed that this improves model's performance on the evaluation set. Now a quick comparison with the existing models in the literature. The literature in the factorization machines is pretty rich, and we have in this table summarized some of the representative state-of-the-art models. Please refer to our paper for a fuller treatment and more lines of work. So after the classic factorization machine paper, the first paper to extend it to the higher order interactions was higher order factorization machines. Deep factorization machine and another paper, neural factorization machines, were two of the early works that showed the benefit of augmenting these networks with a neural network architecture. This was succeeded by attentional factorization machines, which showed that introducing an attention can yet improve models' performance in factorization machines. And then recently we had papers like adaptive factorization networks and deep cross networks, which showed that higher order interactions are better than just the order 2 interaction in the factorization machines, and they also exclusively use neural networks to increase the learning capacity. In this work, we unify the various approaches and propose an efficient attentional architecture which leverages higher order interactions. So in this table, we show the primary results of our experiments. We have experimented with 3 publicly available click-through read datasets and reported the results here on the log loss and the AUC metrics. As we can see in this table, our model outperforms the baseline state-of-the-art models, and in general we can see that the models with higher order interactions outperform the ones with just order 2 interactions. Again, please refer to our paper for a more detailed explanation of the design choices and various ablation studies. To conclude, in this work we have proposed a unified model which combines multiple layers of attentional interaction, and it explicitly captures higher order feature interactions. We leverage a neural network to capture implicit higher order interactions which might not be easily learned using factorization machine architecture alone. Our model scales linearly in maximum number of interactions to be modeled, and thanks to the sparse attentional structure, we are able to pronounce non-important terms, and this further improves the performance. The proposed model outperforms the state-of-the-art models on CTR datasets on various metrics, and one of the table we just saw in the previous slide. One of the problems with our architecture is that it has quadratic complexity at each layer, as we compute all the pairwise interaction terms explicitly. We plan to address it as part of our future work. Thank you.
Excellent, thank you. I see someone up at the microphone if you want to ask a question.
Hey, I was wondering, do you have any data on how fast your model is compared to like DeepFM or DCN? Because that matters a lot for online observing.
Yes. So in our paper, we have the latency comparison as well. While it is slightly slower than the DeepFM architecture, it is still within the permissible limits in terms of latency. That is, among the baselines that we have compared here, our model falls somewhere in between when you look at inference latency on a GPU machine.
Thanks.
And we have a bunch more questions on Slido. So, we have some questions on how this compares with other approaches. Someone's asking, how does this model compare with extreme deep factorization machines, which use CIN for higher order interactions using convolution layer?
Right. So in this work, we have not compared against the XDeepFM paper, so I do not have the exact numbers. One of the reasons we chose not to work with them was because it uses a convolution layer, and in this work we just used a simplified network in which you model each of the interaction terms explicitly. I would think now some of the papers in our work, for example, the adaptive factorization network, they show in their results that they outperform the XDeepFM paper. So we expect our results to be on the same lines, since our model slightly outperforms the adaptive factorization networks. However, I do not have exact numbers for XDeepFM for these datasets.
Excellent. Well, thanks for your presentation. Let's thank the speaker. There's a bunch more questions on Slido that you can answer on the hub afterwards. So.